Hi, my name is Colleen. Welcome to Small Lab, an embodied learning environment. Today we're going to show you how to use a scenario about projectile motion to teach students about the motion of objects in flight and gravity's effect on them. This scenario is important for students to experience because it's extremely difficult for them to conceptualize the independence of horizontal and vertical motion, and additionally to add the complicating situation of different gravitational environments. It becomes very difficult to coordinate all these ideas and come up with a coherent model of how a projectile will behave. Here we see a graph of the vertical displacement of the projectile. You see height in meters of the projectile, time in seconds, and when a projectile is launched, a new graph is made, and you will see that in this phase of the game, the projectile always begins at a height of 1.25 meters. We have a duplicate vertical displacement shown over here for the other students. We have the gravitational field of Earth selected for this point in the scenario, and when you launch a projectile in Earth's gravitational field, it will always take the same amount of time to reach the ground from a fixed height of 1.25 meters. We can select other gravitational environments, for example, Mars, and we see that the gravitational field on Mars is weaker than that on Earth, and therefore the ball remains in flight for a longer time. When Jupiter is selected, the gravitational field is much stronger. We see the ball remains in flight for a very short time, regardless of how hard I hit the projectile. The important conceptual idea that students need to master in this portion of the scenario is that the flight time of the object is linked to the gravitational environment, in this case Neptune, and to the height at which the projectile is launched. Given a fixed acceleration of gravity, the projectile will always travel for the same amount of time. When we change the planet and the acceleration of gravity changes, then the flight time for the object will change. In phase 2, we change the height that the projectile can be launched at. So when I launch a projectile low to the ground, we see reflected here on the graph that it was launched at 0.5 meters, and since we're on Earth's moon, it was in flight for 0.8 seconds. When I launch it from higher, we see reflected on our graph that this projectile was launched from 1.8 meters, and the flight time was 1.5 seconds. One of the nice things about this environment is that it allows you to connect a real-world phenomenon with the virtual phenomenon. So we've dialed up the Earth gravitational environment, and now when I launch the projectile, if I drop this purse at the same time, you should see that the projectile hits the ground at the same time as the purse. Now we're changing the gravitational environment to that of Mars. Ask your students what they might expect to see when a virtual object is launched on Mars while a real object is being dropped here on Earth. Let's try it. What we see is that the virtual object remained in the air for several tenths of a second after the real object here in Earth's gravitational field hit the floor. Now we're moving to Jupiter. Again, ask the students what they'd expect to see when a virtual object is launched and a real object in Earth gravity is dropped from the same height. What we see on our graph is that the virtual object struck the ground long before the real object that was dropped in Earth gravity hit the ground. In phase 3 of the game, we can vary both the height that the projectile is launched at and the trajectory of the initial launch. So if I hit it up, you can see on the graph that the ball travels up before it begins to fall toward the ground. If I hit it down, the ball accelerates straight toward the ground. Now we'll change the gravitation to Earth to see how it looks different. And again, we launch a projectile up. You can see it doesn't travel very far on Earth. Or we launch it down. And you notice when a projectile is launched down, it travels for a much shorter time interval than if it starts with an upward trajectory. So when we change the planetary environment to Jupiter, notice how much initial velocity I need to give this projectile to get it to spend any time at all in flight. Hi, my name is Colleen. Welcome to Small Lab, an embodied learning environment. Today we're going to show you how to use this scenario projectile flight game with your students. The goal of this game is for two students to work together to fire virtual projectiles at a target and, if possible, to strike that target at the same instant. On this side of the floor, we have images of planets. These are planets whose gravitational environments we can choose to play the game in. At the moment, we have Earth selected. On either side of the floor, you see digital readouts for the flight time for the individual projectiles being launched. And here we have levels and points. A level is how many targets have actually been successfully achieved by the players and how many points have been earned. And finally, we have a countdown clock that counts down the action in the scenario. Two players are playing this game cooperatively to earn points. And we take turns trying to hit the target. When the target is struck, the scenario resets, placing the target at a different location. When two students play this game, it's possible for them to earn 500 points if they can both strike the target with their projectile at the same time. This is an important concept for students to master because they must understand that the flight time of their projectile remains fixed at 0.5 seconds, regardless of when they strike the ball or how hard they strike the ball. So in order for both of us to strike this target at the same instant, we need to strike our projectiles simultaneously. Let's give it a try. 1, 2, 3. 1, 2, 3.